So I'm Jian from, here we go. So I'm Jian from UC San Diego. And today I'm going to talk about Orion, a distributed file system for non-volatile main memories and the RDMA-capable networks. So RDMA is coming, it's fast, and it will fundamentally change the storage architecture. In this talk, I want to focus on how we can accelerate remote access for distributed NVMs. So here, it shows that in today's data center, we are basically considering the computation and storage in separate domains. And we simply put the storage into a distributed and over the network, and we just access it remotely. Now, we are having the fast, non-volatile byte-addressable NVM. So this class of memory will have high performance. It will have DRAM comparable latency and bandwidth. It will be byte-addressable and persistent over power failure. Those memory will reside in the memory bus along with traditional DRAM. So now we are facing a situation where we have distributed shared NVMM. And of course, we want to have remote access because this is storage after all. And for accessing remote memory, we have another technology called RDMA, Remote Direct Memory Access. So the idea of RDMA is to provide DMA access between a pair of machines. So it supports two-sided send and receive verbs. And additionally, it should also support one-sided verb, which contains read and write. So a local application can access remote memory without using any of the remote CPU. And RDMA is also byte-addressable, so we can send a message as 1 byte. So let's assume we have fast RDMA network and we have fast NVMM. So can we have fast distributed storage? The answer is not yet. So to compare, we first look at how we access to the local and remote NVM. For local NVMM, we have several NVMM file systems. They are well optimized. And for the remote case, we have to go over a distributed file system. And in this case, the distributed file system is using RDMA network. And this is the performance we are getting. So as you can see, the performance gap is pretty significant in terms of both latency and bandwidth. First, for latency, we are doing a 4 kilobyte write plus an fsync. As you can see, the local NVM file system can perform very well down this less than 4 microseconds. And we are adding over 200 times latency if we do this over the network. For bandwidth, the story is similar. We run file bench, file server workload, and the local NVM performs well as expected, but the remote one can only get between 5% to 19% throughput. Actually, this is kind of expected if you take a look at how those distributed file systems are implemented. They are usually taking an approach where they have a layered design, where the networking layer handles the networking, and the local file system handles the actual file layout. So because they are designed for very slow block devices, they are doing a lot of clever optimizations, but for NVM, those optimizations just cause more indirections. And as a result, it's very expensive to persist because all those internal data structures has to be flushed. A more fundamental issue here is that NVMM is simply faster than RDMA. Let's take a look at just 3 technologies: the hard drive, the RDMA network, and the NVMM. As you can see, the latency for hard drives are just slower than the network, even for the fastest PCIe SSDs. And in terms of bandwidth, it's also within the network's capability. Now we're transitioning to NVMM. Suddenly we're finding that the NVMM is simply faster, like 10 times shorter in terms of latency comparing to RDMA network. And also it's byte-addressable, so it can achieve, if we just issue cache line accesses, we can already achieve the maximum bandwidth. But for networking, we basically need to send MTU-sized messages to achieve that. So based on this fact, we are thinking that the converged storage will be a more common use case. So the converged storage means we run the application along with storage. In this case, it's NVMM. So an additional benefit of doing this is local NVMM supports DAC, direct access, Shen just introduced, which means it bypasses the page cache in the kernel. And however, existing distributed file systems simply do not consider to use any of those local storage. They are basically designed for storage network. And as a result, we have to, if we want to use local NVM anyway, we need to run basically 2 file systems and add another layer of indirection. And it will be very expensive to move the data between those two domains. So those two major issues motivate us to build Orion. The idea is simple. We want to utilize the unique characteristics of NVM and RDMA. So what we should do? The first step is we should not use layering. So we just build a single layer. It's a kernel file system that can do networking. And we call it the Orion file system. Next, we pull the NVMM storage together. So it's like distributed shared NVMM. So now we can let the Orion provide, still like maintain the POSIX I/O interface to the application. So the application will access Orion just like accessing any existing local file system. And under the hood, Orion will provide local DAX access to its local NVM and RDMA access to remote NVM, all transparent to the user. And finally, Orion is intended to deploy in the rack scale, so we need to have good scalability with that assumption. This slide shows the overview of my talk. Although we do support metadata and data replication, and we consider the RDMA write persistency issue, but in this talk, I will focus on how the design works and how we optimize metadata and data communication. This slide shows the overview of Orion cluster. Each Orion cluster has a single MDS, which means metadata server. It runs the actual file system. There is no other local file system. And this file system will keep the authoritative metadata of the entire file system. And we have a bunch of clients. Each of them will also run the same Orion FS, and will only keep the active part of the metadata. Each client will also use some of this DRAM as an RDMA cache. And of course, if you have local NVM, and those NVM is just pooled. The third row here is just data store. A data store is a client that does not run any application. In this case, it's just provide NVM for remote accesses. So by default, the data store does not need to run any application or any code. So the metadata communication in Orion always happens between the client and the MDS. So we are using two-sided RDMA verbs. And for data accesses, we're using one-sided verbs, which means the client will just directly access read or write data stores. So next, let's look at the file system implementation. The file system layout of Orion is inherited from Nova. So Sheng'an just introduced, and let me reiterate a few key points here. So Nova is a log file system. So each inode is a term Linux used to describe the basic the metadata of a file. Each inode contains a metadata log. So each file operation will become a log entry in that inode log. And whenever I do a file operation, I append a log entry, and I do it atomically by updating the 8-byte tail pointer. And that inode log is used to build the in-DRAM structures on recovery. For Orion, we are basically keep the same layout, and we use it like a DMA memory region is a way to register memory for RDMA. So the client will can read the entire metadata region, and it will be able to RDMA the metadata structures by doing a few tricks we described in the paper. For data, it's pretty simple. We just use global addressed pages. So I want to demonstrate Orion using a few very simple examples. First, let's look at open. So let's assume the MDS has 3 files, and the clients do not have the file A, so you want to open it. So the open will become an RPC. The client will allocate an inode and issue an RPC open to the MDS. The MDS will receive that and will do an RDMA write to write back that inode to the allocated space. So now the client already has the basic information, so it can traverse the log page remotely to get the entire log of the inode. I think this is pretty straightforward, and it's a little bit similar to key-value stores using RDMA implementations. Next, let's look at about write. So for write, we we do some, we let each of the clients own some of the pages within this, within the whole address space. And we are describing how we do that in the paper. So here, let's assume the client has owned some of the pages in its local NVMM. It will allocate from those pages and doing a copy and write for the data to those pages. And next, we'll create a log entry and append that to the tail of its local inode copy. And finally, it will commit that log entry to using an RDMA send. The MDS will do the log commit on its own, and finally, we update the tail pointers. Okay, so now we have committed a write. How do we let other clients see that write? In traditional distributed file system, like a lot of we are usually using the push model, but here we are letting the client to pull the update change. So here we call this operation a tail check. A tail check in Orion is basically used to make sure the metadata is in a consistent state. Here, let's assume the file B has been committed by a different client on the MDS. So now the client will do an RDMA read to read the remote tail. This is the 8-byte read, by the way. And it will find that the remote length of the inode log is longer than the local one. We have some mechanism to make sure this exists, this holds. And after that, if you RDMA read the difference and update those changes to its local copy. Okay, so when do we need a tail check? One example can be a read. So when doing a read, we will do a tail check in the background. Because for most of the cases, even you have a new update, it may not affect what I am reading, right? So I just do it in the background. Hopefully nothing has changed, and we will get the log entry from the local inode log. The log entry points to a page that is in the remote data store. We're simply doing an RDMA read to fetch that page back to my own data cache. As you can see, we can update this file write entry atomically. So after that, it will just point to its data cache. And for next write, it will just hit that data cache. For the next read, it will just hit the data cache. And for next write, as I mentioned before, we prefer allocating local NVM first, so it will likely go to the local NVM. So in the long term, both read and write should go to local NVMM. Okay, so that summarizes the basic file operations. So we are designing the way we communicate metadata based on two observations. The first one is RDMA can handle inbound operations better. The inbound operation means the MDS is handling incoming RDMA reads. It does not need to do anything. The NIC will basically take care of everything, and this can be done in a very scalable way. For outbound operation, for example, the MDS need to write to the client. This is not scaled as well as read. And the second observation we have is RDMA prefers small writes. Because of the access and latency is already so low that we are talking about individual PCIe transactions. So a smaller write will involve fewer transactions and hence has lower latency. And this is a little bit different from traditional TCP IP networking. So let's look at what we have done with the metadata communication. We have tail check, which is the 8-byte RDMA read, and this should be the most common case, and this should be the most efficient one. But also, we cannot do much because this is just RDMA read. Next, we have log commit. A log commit is usually can be done within 2 cache lines, so it's using an RDMA send. It should be fast, but we want to make it better. And the RPC is basically the fallback case. It involves for other operations such as open, and also it's used for operations that involves multiple inodes such as rename. These are less common, and we will just leave it as is. So we want to optimize log commit. We're using a technique called speculative log commit or client arbitration described in the paper. So the idea is we just return when the RDMA send completes for a log commit. So here, I mean the RDMA send verb is signaled. So at this point, it arrives to we can guarantee we are using reliable connections. So we are guarantee that MDS will eventually receive that log entry, but we just let the client resume. And after doing this, we need to do a tail check before send. But the send is usually more expensive than tail check anyway, so we can hide latency. And when there's a conflict, we need to rebuild the inode log. And finally, we use RPCs for operations that have set defects. For example, if you append a file, it will change the size of the file, so we're doing that via an RPC. So let me walk through an example here. We have two clients accessing the same inode, and the client 1 will create a log entry 1 and issuing a tail check. Okay, it found that the MDS is having the up-to-date, we are having the up-to-date tail as a MDS. It will commit that log entry to the MDS and resume. At the same time, client 2 is doing another log append. So before doing that, the MDS already committed its local log. So now, when it do the log tail check, it will find, okay, the remote log has been updated, and I need to fetch that log entry. And if there's no conflict, we'll just resume committing the log entry number 2 to the MDS. But now, at the same time, client 1 is doing another log commit. But this time, the RDMA returns the pointer that is consistent with local because the log number 2 hasn't been updated. So if we just go through, just resume. But remember, we are only using this for file operation that has no set effects. So at this point, it does not make it's still a consistent state. It's still an eventual consistency state. The client A will now have log entry 1 and 3, while the MDS will eventually have 1, 2, and 3. Okay, for the next write, the client will do a log tail check again. Okay, this time we need to pull some data. But after that, it found that, okay, I have a duplicate log entry number 3. And we have other cases that will indicate a rebuild. So in this case, we need to reread the log page and rebuild the inode log. So by doing this, we can make sure the log commit and the persist can be done within 500 CPU cycles. So persist here means we do the cache flush plus sfns. Okay, so we implement Orion prototype in Linux kernel, and we basically we add 15,000 lines of code in addition to Nova. And we use the RDMA stack from Mellanox. To demonstrate the case for converged storage, we bind each client with a single core for all of the networking operations. On each of the node, we have a 2-socket machine, and using 16 GB as DRAM and 32 GB as NVM. And we're using a Mellanox InfiniBand card as the NIC and have a InfiniBand switch as the top of the rack switch. The first slide shows the basic file operation performance. So it's showing the access latency. On the left side, we are comparing with distributed file system. As you can see, overall, we are getting much better performance than existing distributed file system, ranging from 1.3x to over 100x. On the right side, we are comparing with Orion to local file systems, such as Nova and ESE4. As you can see, we are not losing a lot, but remember, we're a distributed file system. So we are only having 1.3 to 3 times latency comparing to Nova, which is our baseline. Next, we run some applications. As you can see, we run FileBunch and MongoDB with YCSB workload A, and we compare the results relative to Nova, so the 1 means the Nova throughput. As you can see, we can get 68% to 85% comparing to Nova, and we are much better than Ceph and Gluster, which are the distributed ones. And finally, we are showing you the metadata access that I just mentioned. So we compare the 3 types of metadata operations over 10,000 inodes. As you can see, the tail check scales pretty well. The other 2 still has linear scalability, but it's worse than the tail check. On the right side, it shows the actual number of operations per second we can achieve with 8 clients. As you can see, we can achieve around 14 million tail checks. And for log commits, we can do around 2 million, and for RPCs, we can do less than 1 million. And this all matches our expectation to those metadata operations. To conclude, to answer my question at first, how can we accelerate metadata access? We should use local NVM. So Orion is designed to fix the issue with existing distributed file system where it does not have NVM support, it does not have local memory support, and it has significant software overhead. We unify the file system layer and the networking layer to provide fast metadata access. And we allow DACs to local memory while participating in the distributed system. And our performance shows Orion is comparable to existing local NVMM file system and outperforms the distributed ones by a large margin. And that concludes my talk. I'm happy to answer questions.
All right, questions?
I have a question for the optimistic log commit.
Mm-hmm.
The reason that you are using, first of all, is 128 byte, so it's relatively small.
Yes.
It makes sense to use one-sided RDMA.
It's actually two-sided. It's still a send.
I know that.
Yeah.
If you use two-sided, is that only
It's an unacknowledged RDMA. But I think you get my point. Yeah.
But yeah, okay, sure. Then does it make sense to use atomic verbs to change the tail pointer?
So you are talking about RDMA atomic, right?
Right.
Because RDMA atomic doesn't really work in the persistent domain. So it only works from the visibility standpoint.
That can be, that works in the system that will change that.
Oh, so if you can provide efficient atomic RDMA verbs, that's definitely one of the directions we can look into.
Sure.
Yeah.
A nice talk. And I have a question related to the result when you compare your work with like Ceph and MongoDB. For those database or file systems, are those RDMA enabled, or it's just like the regular based on the Ethernet?
We are all using RDMA transport, and we are not using IP over InfiniBand. We are using the whatever RDMA transport they are providing.
Okay, thank you.
In the front.
Tom Telby, Microsoft. So this is really interesting stuff, and I really like the idea of integrating RDMA into a file system. I think that some of your concepts would actually apply to other generic file systems. I would challenge you to think that through, because the layout and the integration are obviously highly optimized, but the basic idea of obtaining push mode and pull mode is really powerful. In particular, I think you could sort of hide the RDMA layer with this solution. You could, for instance, register a file instead of registering memory. You could perform RDMA operations to the file instead of to memory, which was then forwarded to the file.
Yeah,
so
actually,
I'd ask if you've thought about these sorts of generalizations of your concepts outside of Orion itself.
I think that's very interesting, and we are actually looking into those kind of applications. So apparently, like the Orion only works as a POSIX interface, and there are many applications that do not want to use POSIX. And for those applications,
POSIX is getting a little long in the tooth for this stuff, by the way. But yeah.
Our argument is it will still exist for a long time.
That's good.
So,
that's laudable. I like that.
Yeah. So we are definitely looking into other directions.
Okay, thank you.
Hi, I'm Jian from ASU. I'm just curious if you have compared your work with the existing works like Octopus. It's also a distributed NVM file system.
So we actually have data for Octopus. It's a little bit tricky here because, oh, sorry. Let me find we'll just go through. Okay, here is a more complete comparison. We have Octopus here, but the issue with Octopus is that it's a user-level file system, so we have to use fields. And also, it's designed based on the hash table, so which means it has some constraint to the file system layout, and we cannot actually run, for example, file bunch on Octopus. But yeah, but we did compare that in the paper, and we have some discussion on like why we design a different, like we're using a different design.
Okay, thank you.
Ceph is going to be making the writes to the journals and to the objects safe from failover. And so all of this data needs to be replicated, whereas in Orion, apparently all the writes are to a single NVMe. So I'm wondering, so Orion is good for showing us kind of a theoretical best case scenario, but what I don't see in this work is how we're going to be handling failures in the devices themselves or in the metadata server. And that's where a lot of the overhead we're seeing is going. So I'm wondering, how do you see your work, the performance of Orion changing when you need to take into account failures that are commonplace in a distributed system?
Okay, so regarding, I think this is like two-part question. The first part is how do we handle reliability, and second is how do we detect failure. So the first one is Ceph use like basically the Ceph is like the core idea of Ceph is using their like the thing the crash is like one of the basically the core pillar of Ceph. We are actually doing both data and metadata replication. It's showing in our paper, and we have the evaluation. So we are actually not adding a lot of overhead when doing replication over RDMA. So from this regard, I think most of my points still stand. For the failure detection and failure recovery, that is also like part of the design of our system. I think the major issue here is we are implementing in the kernel, so like a crash will have more. Basically, you need to like deal with more issues. So it's one of our future direction, but like the failure recovery is part of our design, and this is a very like first step of the project.
Okay, thank you.
All right, all right. Quick question.
This is Jian Fu from NODT. And I just saw you talk, there are a lot of communications with metadata server. Do you think it's scalable well? And I see there is experiments, maybe in your last slide, you said it scales well. Is this for, is this a bare metadata server, or you have considered your local active metadata?
Sorry, I don't get your last sentence.
Yeah, I mean, is this experiments from just access only the metadata server, or you already consider the local active metadata?
We do both. Like this is basically letting 8 clients issuing real like tail check, lock commits, and RPCs. So they have to consider their local copy. And also we are trying to push, this is like basically a kind of extreme case where we just push those lock commits to the MDS, and it should demonstrate the worst case of the system, at least within like 8 nodes.
So do you still think the metadata server itself is, it will scale well? So
if you're talking about like a rack scale or a reasonably, like where the case is like you are doing,
since it's a distributed system,
so if you're talking about like data center scale, then I think my short answer is you need indirection. You need like either partition or you need another indirection layer to do this. Actually, like if you consider this, Orion is basically a very low-level kernel file system. You can even mount NFS on top of it, right? So it's like if you're talking about data center scalability, so first, I don't think they have the need for convert storage because like each node will only have a tiny portion of the entire data volume. So I guess in that case, you need some additional indirection layer on top of Orion.
Thank you.
All right, let's thank our speaker.